Hello and welcome to ECEN 215, Principles of Electrical Engineering. Today we're going to talk about the circuit elements and Ohm's law and just some basic circuits that we're going to analyze. This is our third topic in the class, and this again is still a little bit of a review of what you would have learned in physics. So let's go ahead and get started. So now let's talk about circuit elements. So we've kind of been seeing these devices, element A, element B, element C, element D, E, so on and so forth. So let's talk about the different types of elements we have. So we have, for instance, here we have power generating devices, power supplies, if you will. Um, Part A here, element A, is a 12 volt DC voltage source. So this would be equivalent to like your car battery, for instance. It provides 12 volts constant, flat. And of course, in all reality, it does have some variance over time, but for all practical purposes, it is DC, has zero frequency component. And from a sense of a circuit analysis, that's how you would treat it. It's flat DC is DC no matter what. And since these are considered ideal elements, that means that it will provide 12 volts no matter what. And what we're going to talk about is when we get into Ohm's law in a few moments, where if you put a short circuit across this power supply, in other words, you draw a wire between this terminal and this terminal, this thing would provide infinite current. In other words, the voltage across this power supply, an ideal power supply, is always the voltage specified. So this power supply would be 12 volts. It always will provide 12 volts across the terminal, no matter what you connect to the terminal. Now, in the real world, in a real application, that is not always the case. If you have a 12 volt battery and you take a wire and you short it across, either the wire is going to explode and disintegrate, which usually is the case, or the terminals of the battery are going to disintegrate and blow up. And I have actually seen lead acid battery blow up, so it does happen. So it's you can melt the terminals and pretty much destroy a battery. So that's real world. Now in the circuit analysis, we actually view this as an ideal power supply. So it will provide infinite current at 12 volts. Whereas here we have an AC voltage source. So this power supply here instead does the alternating voltage. If you will, the average voltage of the supply is 0 volts. And in this case, it's going to produce 5 volts times cosine 2 pi t, where this is, if you will, a frequency component. And this, as time goes from 0 to infinity, the cosine is going to change, and you're going to end up with an alternating signal that has got a magnitude of plus or minus 5 volts, because the cosine term is going to be plus or minus 1. So here, like we had a moment ago, we had constant, we had circuit elements that were voltage supplies. These are current supplies, and this first one here is a constant DC current source. What this current source is going to do is produce 2 amps, always going through it. Again, this is an ideal DC current source, which means if I hook a wire from here to here and short circuit, in other words, the resistance, if you will, connected to here is 0 ohms. This is an ideal power supply. And I would probably highlight that this is probably a good slide to remember, because I usually have a test question dealing with this concept of ideal power supplies. So for instance, if I have 2 amps and I hook a wire, and let me just switch over to a pin here, and if I have a short circuit and I connect this to here, where this is 0 ohms, HMS. So we have 0. There's nothing going through here in a sense of resistance. The current that is going to loop through here is equal to 2 amps, no matter what we do. That's always going to be the case. So, a particular question to be is, if I have an ideal current supply, and it's at 2 amps, and I put a 0 ohm resistor across that current supply, what is the current? It is 2 amps. What is the voltage across there? Well, we're going to cover that in a moment. It's Ohm's law, and we'll cover that in a second. So those are the things that you're going to want to remember for the test. Um, so in this case here, we have similar as to the AC voltage source, we have an AC current source, the same concept. 3, in this case, it's a sine. Typically, it's cosine, but in this case, it's sine, which means it just shifted 90 degrees versus the signal we had before, 100 pi t. So this is going to produce a current in the same way. So depending on what else is connected to the circuit, you'll have different voltages and stuff going on, but the actual current that is going through the supply, in this case, is 2 amps. In this case, it's 3 sine 100 pi t amps. These type of circuit elements are dependent sources, meaning that they depend upon other voltages or currents to do its element. So in this case, this power supply here is a voltage controlled voltage source, and it's going to generate a voltage that is 2 times Vx. And usually you will see in the schematic of reference where Vx is defined must be set. So in this case, Vx is considered the voltage across this element here. So the voltage here is going to be 2 Vx, and you would have to figure out what Vx is, and you would insert that value into this equation. Same thing here in the case of a current controlled voltage source. In this case, so this is a voltage source signified by the plus and minus sign. In this case, it's going to be voltage will be 3 times whatever this current going through this element is, so in this direction. So if this current is 1 amp, then this power here would be 3 volts. If the current actually was flowing this direction in the opposite way, with the arrow being this reference, in other words, this is now, say, 1 amp going this way, you know, in the opposite direction of the arrow, then it would be 3 times minus 1, or minus 3 volts. And this is dependent current sources in the same vein. We have a voltage controlled current source, so it's 3 times Vx amps. So if Vx was 5 volts, this would be 15 amps going this direction. If Vx was minus 15, then you would have, or minus 5 volts, then you would end up with minus 15 amps going in the opposite direction. So you would have the current actually flow in the opposite direction. And then, of course, here we have a current controlled voltage source. In this case, whatever this current is, it's just going to be an amplified version of that. So if this was 3 amps here, you would end up with 6 amps here. So what is resistance? Resistance is, again, dealing with the cross-sectional areas. So resistance is a constant times the length of the conductor itself, length of wire, length of a trace on a circuit board, so on and so forth, a length of any type of conductor, times the cross-sectional, or divided by the cross-sectional area of that conductor. So if you have a wire and you have a larger cross-sectional area where A increases, that is going to decrease proportionally the resistance when it only figures, because when you use heavy gauge wires, it's known, which is actually a low number, like double wire, or the wiring that's like in your house or apartment is probably like 14 gauge wire. That is a larger diameter wire than really thin wires that are like on a circuit board or hooking up to the screen on your smartphone, things like that. So the A is substantially different. And the longer the wire is, the obviously more resistance the wire or conductor has. In a case of like power lines taking a long distance, you know, the resistance on that wire traveling miles and miles from the power plant to a substation, that L becomes an important factor in determining how much power loss is actually occurring in the circuit line. So R, the resistance of a conductor, is related to a constant of L over A. Conductance is simply the inverse of resistance. It's just 1 over R. And it has units of Siemens instead of ohms, and is denoted by I is equal to G times V for a simple term, or 1 over R. Which brings us to resistance tables of all the different types of conductors that are out there, and there's a whole lot of these, and you can determine the rho, if you will, the ohms per meter for all sorts of different conductors: aluminum, carbon, copper, gold, for instance, silver, tungsten. Um, so as you can tell, gold is very ideal, and it's actually heavily used in a lot of circuits, actually, gold plated. Um, and obviously things like Teflon in glass times 10 to the 19 ohms as an ideal insulator. This brings us to Ohm's law. This equation is pretty much going to be the main equation for the entire semester. This equation is simply V is equal to I times R. It is the relationship between resistance and current, and it's all determined by the simply voltage and resistance, or voltage and current are related by resistance, and it's linearly at that for a standard plain resistor. So we represent resistor by the symbol, this back and forth kind of a squiggle. That resembles resistance. It means it's going to resist current flow, and when something resists, it's going to build up a voltage. And in case of the fluid analogy, we're going to build up pressure across an orifice. For instance, if I'm pushing, so many gallons per minute through a tube, and the tube has an orifice, there's going to be a back pressure that is caused by that. Well, the same thing's happening here with the resistor. So we're forcing current through the resistor, and that force is going to result in a voltage. And that relationship is Ohm's law. So this is probably the one slide of this entire slide deck that is probably going to be copied and used heavily throughout the semester until you get these equations basically constantly memorized. So, simple algebraic equation: I is equal to V over R, V is equal to IR, or R is equal to V over I. And correspondingly, if you are looking for power, which we defined earlier, is equal to V times I, in other words, the voltage times the current, then power is VI. Or you can correspondingly, if you know current and you know the resistance, you don't necessarily need to compute the voltage, because we just simply use IR, and that ends up being I squared R. And hence why this is where the level of current going through a wire is a very important thing. If you ever wondered, if you probably know this, that actually the voltage is going through high voltage transmission lines, taking the power to and from a generating plant to a city, for instance, is not done at household voltages like 240 volts. It's actually done at like 500,000 volts. Well, this right here is why. If you ever wondered why they use hundreds of thousands of volts of energy, of all of that charge being built up, and why so high a voltage, is because we're trying to lower the I squared component, because the power loss is related to the current, really proportional, times the resistance. Whereas you notice here, power is V squared over R. So if we have more current going through a line, then the more loss we're going to have in that particular line. So what they do is they make as good a conductor as they can, and they boost the voltage up to withstand that. And so they have insulators that can handle, hundreds of thousands of volts. So these are just some simple circuits. For instance, we have a power supply, the circuit element 10 volts, and a resistor across is 5 ohms. So normally I would hop around the class and ask random students what the values are. So if we have a 10 volt power supply here, and we got a 5 ohm resistor, what is the current going through the resistor? Well, we have 10 volts divided by 5 ohms. And it's equal to 2 amps. So we have 2 amps that is traveling from the positive to the negative, and it's constantly doing this. And we're going to actually write the equations for this in the next lecture when we start really going into or in the next couple of lectures when we start really using these current and voltage laws. So these circuits right here just kind of give you a fundamental flavor. So the KVL requires that VR is equal to 10 volts, because the 10 volt drop here must equal the 10 volt drop across this. So we know that this is 2 amps. So that's how we get that. And then of course we can also use KCL and do the same thing. And we come up with all of this. So here we have another circuit we have defined as a 25 volt power supply with a 25 ohm resistance. We've labeled I1 going into the power supply, and we also have I2 So we have I1 is what's going in the power supply, and we have I2 is coming out of the resistor. We labeled V2 as this positive and this is negative. And so the question is what are the values in this case? Now we're going to solve these things based upon the convention that we have outlined in this drawing. So that is very important that we do that. So in this case, let's take a look at this one by one. We have 25 ohms and we have 25 volts. Well, so immediately we know it's going to be 1 amp because the 25 volts is going to be the 25 volts that's going to cross the resistor. So this is very similar to what we just did. However, what is the current? Well, in this case we have V1 is equal to 25 volts from here to here. V2 is equal to minus 25 volts because it is flipped the other way because of the positive sign. So the current going from here to here, which is I2, is equal to minus 25 volts divided by 25 ohms. So the current going from positive to negative this direction, so just to kind of draw it here. So the current that's going this direction, I2, is equal to, with corresponding using this V2 right here, that convention is equal to minus 25 volts over 25 ohms. Excuse the drawing. It's equal to 1 amp, right? But it's minus 1 amp. So that's I2, which means that if we were trying to do positive convention, that's really telling us the current is really going this direction, which is what we really expected. But the circuit analysis called for us to use this I2. So this is equal to I2, right? Now what is I1? Well, if we use the Kirchhoff current law, we look at the nodes. Well, this is all one node right here, and this is all one node right here, and there's no hidden charge in the node. There's no hidden current anywhere, which means what? It means that I1 is equal to I2. So we can say that. So one way we could do this, and else is also if we want to measure the actual voltage and stuff, is actually use an amp meter and a voltage meter. So if a voltage meter, your digital multimeter, and usually this part of the class, I actually physically bring a voltage meter into class so you can see it. So I don't know if you've ever seen one in person. You probably, depending if you worked on vehicles before or something, you probably own one. Voltage meter, you would take a measurement across circuit A. So we have a circuit here, element A. Let's just pretend that is a resistor or something, and we want to measure the voltage across it. Well, if the voltage across it will be this, because this is positive and negative here, right? And so we're going to say, pretend for a moment, this is going to read 12.0, and that's going to be in volts, right? So if there's 12 volts across segment element A, we would read 12.0 here. So that's what the voltmeter does. Now, say there's rest of the circuit is here and there's current flowing through A. So for the purposes of argument, let's just pretend that the current is going this direction. Okay, similar to what we just did a moment ago. So the current is going that way. Now, let's just say the current going through circuit element A was equal to 3 amps. Okay, if we have 3 amps going through here, through some sort of unknown thing that is connected here, whether power supply, whatever it may be. It could be another power supply. So there's some other circuit element here that is unknown. We'll just draw it a box, right? I'll just put a question mark in it for right now. So we have some sort of a device connected power supply that's driving this current 3 amps through circuit element A, and we'll just pretend A probably is a resistor, right? So we have 12 volts going across it, and we have 3 amps going through it from positive to negative. So one thing we can immediately tell is if I asked you how much power was running through this, what would your answer be? It'd be 36 watts because 3 amps times 12 volts. So we have 36 watts going through whatever 36 watts is being absorbed, or is it being generated? Well, as we go back to the earlier slide, we learned earlier that if current is going in the positive terminal and leaving out the negative terminal, then it's being absorbed. So we can immediately say that we have 36 watts, so P is equal to V times I, right? Which is equal to 36 watts. And it's being absorbed because it is going in the positive and leaving the negative terminal, right? So we have that. So we know those two things. So what do you think is on the amp meter screen? Notice the direction of the amp meter. The amp meter here we have as negative and positive. Now, do you think that really matters? Does the amp meter care? The amp meter actually doesn't care which way you do it, but if you're reading it for the purposes of knowing the current, it does matter. If you have a kind of a standard digital multimeter, you usually have a red wire and a black wire, which is labeled common for the black or ground. And the red wire is going to be kind of like loop in or current in. And there's usually a separate post for the current versus a voltage. So there's usually multiple posts on your digital multimeter. So usually the black wire is considered the negative lead and the red wire is the black lead or the red lead. And so you hook it up, and if you wire it up like this, but we have 3 amps that is actually flowing through, right? We are going through this direction. We're flowing current through as in the direction of the arrow. So the amp meter is going to read, what do you think? It's going to read minus 3 amps because the current is entering the negative terminal and leaving the positive terminal. So the convention on the amp meters, if you will, backwards for the way of the circuit, the way we've got this example set up. I mean, if we reverse this where circuit element A was a power supply and current was going the other direction, if power was flipped around, then the current meter would then read the other way. It would read 3 amps. So just to kind of do that illustration, if we delete this, let's kind of clean this up a little bit. And we still have our 12 volts, let's say, but instead now we have current that's flowing this direction for purposes of argument. And just say it's the same 3 amps. So voltage meter now is still reading 12 volts correctly. And now the amp meter is going to read 3 amps. Because now we have said that this circuit is pushing current this direction. Which means what? Are we still doing 36 watts? Yes, we're doing 36 watts. Are we absorbing or are we generating? In this case, we're generating because now the current is entering the negative and leaving the positive. So this is where it flips. In this case, the current enters the negative terminal and is leaving the positive terminal of the circuit element, flipping basically. And in that configuration, it's generating. It's a power supply. So that's very important that you get confused on this point where you watch this slide, ask questions on this, but this is where several students get a little baffled on whether or not something is generating or absorbing power. So in summary, today we have learned basic circuit elements, things like DC and AC voltage supplies, DC and AC current supplies, dependent current sources, dependent voltage sources, both dependent upon either a current or a voltage as the input, if you will, the control element or controlling variable to that. We've also looked at resistors. Here in a few topics ahead, we'll be discussing inductors and capacitors, so all sorts of different elements. There's also things like operational amplifiers that we're going to go over later in the class as well, diodes, transistors, all sorts of things that are circuit elements in the end. Those circuit elements all are corresponding to the voltage and the current that is going through them. We discussed Ohm's law and simply R is equal to V over I. Or you could also say V is equal to I times R, so on and so forth. Ohm's law is the governing equation of everything that's going to be foundational in this class. So it is, I would probably say it is the one set of equations, really the one equation in the end. You just have to learn one small equation will govern pretty much all the work that you have ahead of you in this class. So it's very important that you understand Ohm's law fundamentally and apply that. And of course, correspondingly, we have the power equation, P is equal to V times I, and hence through Ohm's law in that equation, we're able to get equations such as power is equal to I squared R and V squared over R. Again, very useful equations to know because one of the very common questions being asked in the homework and in some of the test questions is what is the power in resistor 5, or what is the power being supplied by the 5-volt power supply, things like that. And you need to know both the current and the voltage to be able to solve for that. And of course, we reviewed some very basic circuits, one resistor type circuits that just applied Ohm's law. So you can actually see if given this resistance and this voltage, what's the current, or given this current and this resistance, what's the voltage across the resistor, so on and so forth. They're just applications of Ohm's law.